Let's take a minute to revisit the Atwood's machine. So you recognize a system that looks like this one. Let me make up some values and say that mass number 1 is equal to 2 kilograms and mass number 2 is equal to 5 kilograms. The typical question here would be, what's the acceleration of the system when released from rest? So there's a few ways we can do this. One approach is to make a free body diagram for the entire system. Another approach would be to make 2 separate free body diagrams for each individual part of the system. So let's try that approach. We know that the system's going to accelerate overall in this direction. So there has to be a larger upward force on block number 1 than its downward force. So what's pulling down? The weight of block number 1, which we can find by multiplying its mass times acceleration due to gravity, and then tension pulls upward. And we might argue that since it's just one piece of string that wraps all the way around, then the tension is the same throughout. So whatever tension is pulling up on block number 1 is also the same tension that pulls up on block number 2. So I draw that vector of the same length for each of the 2 objects. But being 5 kilograms, block number 2 has a much larger downward pull, so large that it exceeds the upward force, so the net force on block number 2 will be downward. So when we apply Newton's second law, the sum of all forces on each individual block has to be equal to the product of mass times acceleration. Or in other words, when I take the difference between the upward pull and the downward pull for block number 1, I can set that equal to its mass times the acceleration of the system. And for block number 2, it's the same thing, except the larger force is the downward force, tension is the force opposite the direction of motion, and I set the difference between those 2 forces as the net force equal to m2a. If I take these 2 equations and add them together, then t and negative t cancel out, and what you find is m1a plus m2a, right? m1a plus m2a has to equal m2g minus m1g. This should all be review. When we simplify, we get a is equal to g times m2 minus m1 divided by m1 plus m2. In this example, a would be equal to 9.8 meters per second squared times 5 minus 2 over 2 plus 5, or in other words, times 3/7. And if you calculate 3/7 of 9.8, you should get a number of 4.2 meters per second squared. Okay, so what does all this have to do with rotation? Well, we took a very simplified look. The only way that the tension pulling up on block number 2 would equal the tension that also pulls up on block number 1 is if that string passes over the top of the pulley without binding, so to speak, with the pulley. In other words, what we're really imagining is that the pulley doesn't rotate, but rather maybe the pulley is made out of really smooth plastic and the string is made of silk, and the string passes without any friction and slides over the perimeter of the pulley. But that's not really how pulleys work in general, right? Typically what happens is there's some amount of friction between the string and the pulley, and so the string binds with the pulley, and there's no slippage between the string and the pulley, and instead it causes the pulley to rotate. So if we think about what's going on in terms of the energy, as block number 1 rises, it gains gravitational potential energy, and it also gains kinetic energy. As block number 2 falls, it loses gravitational potential energy and gains kinetic energy. But both those energies are translational kinetic energy. The 2 blocks just move along straight line paths. However, the pulley, well, if the string just slips over it without making the pulley rotate, then the pulley doesn't gain any form of energy. But if the string really does bind with the pulley and has a force of friction with it, then the pulley rotates and it gains rotational kinetic energy. So that's another way that we can approach this problem. The loss of gravitational potential energy of block number 2 is the fuel, so to speak, that produces the gain in all these forms of energy. The gravitational potential energy of block 1, the translational kinetic energy of block 1, the translational kinetic energy of block 2, and the rotational kinetic energy of the pulley. And so that's where our new information that we're studying in this unit comes into play. We have an equation for the translational kinetic energy of block 1. It's 1/2 m1 v squared. The kinetic energy of block number 2, 1/2 m2 v squared. The rotational kinetic energy of the pulley is 1/2 I omega squared. And so the question goes, well, what's the value of I for a pulley? I'll give you a formula, and we'll explain that in another video where it comes from. But for now, I'll tell you that we can calculate the rotational inertia of a pulley. Oh, and we're going to assume that the pulley is made of solid matter. In other words, it's not like a bike wheel where all the weight is on the perimeter and then there's very lightweight spokes that attach. Instead, we're going to say it's just one like solid block of wood or plastic or something like this. In the case of a solid cylinder, we calculate its rotational inertia by multiplying its total mass times its radius squared and then dividing that by 2. Whereas if all the mass was located out on the perimeter and the interior was hollowed out like a bicycle wheel, minus the spokes, then we say the rotational inertia is mr squared, and we don't divide by 2. Stay tuned for a future video where we derive these formulas. For now, it's good enough to note that I is equal to 1/2 mr squared for our pulley. Okay, so let's set the problem up a little more. I've given you the mass of the block as 2 kilograms, the other block is 5 kilograms, and let's say the mass of the pulley itself is 1 kilogram. In our first approach, it didn't matter. We didn't need to know the mass of the pulley because the pulley wasn't rotating. But now if we assume that it really does rotate, we're going to have to take that into account. So here's how we might solve the problem in this case. Knowing that the loss in potential energy of one object becomes all these forms of mechanical energy increase, we can state that mathematically. M2 times G times H. Let's illustrate the picture a little better to make sure we're labeling what we're talking about. So, snapshot number 1, block number 1 and block number 2 are positioned here, and then in snapshot number 2, block number 1 has come up some distance, block number 2 has gone down some distance, and if we create a reference line, we can say the distance it's fallen is h. And by the way, as long as this string is not made of some a bungee or elastic type material, then if we compare those two, that would also be the same value of h. Okay, so m2 times g times h, that was the loss of gravitational potential energy of block number 2. That loss of energy becomes the increase in energy for block number 1, so m1gh, plus the kinetic energy, translational kinetic energy of both blocks, plus the rotational kinetic energy of the pulley. Okay, so let's label that as step 1, and then just see if we can derive a tidy equation for this whole expression. So moving on to step number 2, we're going to make some substitutions and simplify a little bit. We'll say m2 times g times h is m1 gh plus 1/2 the quantity m1 plus m2 times v squared. We're factoring out the v squared, but I'm also going to make note of some kinematics. We're going to say the initial velocity was equal to 0 as it descends a distance of h to reach a final velocity, v squared equals v initial squared plus 2ax, or we can call it in this case 2ah. and v naught is 0. So I'm going to replace v squared with 2ah. 2ah plus 1/2, and then rotational inertia of a solid disk is 1/2 times the mass of the disk times its radius squared, and we multiply that times omega squared. Okay. M2 minus M1 quantity times GH equals 1/2 M1 plus M2 times 2AH. We can cancel the 2 and the 1/2 plus 1/4 M R squared, and then we'll replace omega with V over R. We learned in a previous lesson for an object that moves along a circular path, S is equal to theta R. R is the radius of the circle, obviously. Theta is the angle subtended as it displaces from point number 1 to point number 2. If we take the derivative of both sides of this equation, d dt of S is d dt of theta R. Well, ds dt is the speed along the perimeter in meters per second. R is a constant value, so you're left with d theta dt, but that's omega. So if v equals omega r, then omega is v over r, and that's the substitution that we've made here. On to step number 4.